with the laws of refraction, now we come to a term which is called refractive index. Refractive index, in a way, kind of property of the medium itself. Light enters from one medium, bends in the another medium. So now before we discuss refractive index in detail, we will try to understand why and how light is bending from one medium to another medium. For this, we will take a simple analogy where you have to reach from, let's say, point A to point B, and in between the medium changes, which is affecting your speed. Like if it is ground, it's water, and again ground. Something like light is passing through the slab where in between the medium is changing. So normally the principle of least time, if we want to reach from point A to point B in minimum time, the best way is to go straight, the straight line between 2 points, like something like this. When we are traveling in one medium. But here in this situation, what will happen? We know that we will move faster in the ground compared to we move in the water. So what we will do, we will start from this point. As soon as we reach the interface of ground and water, we will try to shorten our path because speed is minimum. So we will try to shorten our path in the lower medium. So we will move towards the normal. That will make the distance covered in water minimum. And then again at the other side of the interface between water and ground, we will move away from the normal to reach to point B. Something like this. Clear? Because our speed is different in different medium, to reach between 2 points in the least time, we will alter our path so that we will try to cover more distance in the faster medium and less distance in the shorter medium. Something similar the light does. So the similar behavior of light is given by Fermat's principle of least time. It says that light will always choose the path from 2 points where it will take the minimum time to reach. The analogy which we have discussed makes it clear that why light is changing its direction or why light is bending when it is entering from one medium to another medium. Now we will go to refractive index. The first thing we learn in the laws of refraction, which says Snell's law, sin I upon sin R is a constant, and that is the refractive index of the material. So we can see Snell's law in a little different way. The similar thing, we can say sin R is proportional to sin I for two medium. What I am trying to say, if you increase the angle of incidence, the angle of refraction also changes. Okay, something like this. In this case, if you are increasing the angle of incidence, because refractive index is constant, then we will find a larger angle of refraction. So sin I upon sin R will always be a constant. Snell's law also helps us to understand one more thing, that is, if n number of lights, like here if it is ray 1, another ray 2, which is parallel in one medium and enters in the other medium, after refraction, both the lights will be parallel to each other. Okay, so Snell's law is giving us two indications about the relationship between I and R, and the light rays which are falling parallel will remain parallel after refraction. So if we talk about sin I upon sin R is a refractive index, we can say this is the way it is refractive index is measure of bending of light. Because sine, we know sinusoid is something like that. It starts from 0 and goes in the first quadrant if we talk about 0 to 90 degrees. So if the value of I will increase, the value of angle will increase, the value of sine also increases. So here it is clear that sine I is indicating bending of the incident ray and sine R is indicating bending of the refractive ray. Now here if I say n is bigger, if n is bigger, this indicates that sine R is smaller. Okay, sine R is smaller compared to sine I, then only n will be bigger. So this implies that refractive index, when light enters from one medium to another whose refractive index is more, the sine R is smaller. Okay, if the refractive index of this medium is higher compared to this much, the refracted ray will move towards the normal more and more. Okay, and if the other case, if we see the case otherwise, when the light enters from a medium of higher density to lower density, what we will find that if it is the incident ray, what it will do, sine R, so also the angle R will be bigger. So we can say when it is entering from faster medium to slower medium, the refracted ray is bending towards the normal, and when it is entering from slower medium to faster medium, it is bending away from the normal. The analogy of ground and water fits in here as well. Faster medium, we will try to cover maximum distance. In the slower medium, we will reduce the path length. Here in the slower medium, we will move, and in the faster medium, we will take the longer path. We can understand refractive index in terms of velocity directly, which will be the measure of change in velocity, will also be indicated by refractive index. Here, the same example, medium 1, medium 2, light ray is entering from here and it is bending towards or away from the normal. So refractive index here will be relative, that will be n21. Refractive index of second medium with reference to the first medium will be given by velocity of the light in first medium divided by velocity of light in the second medium. Similarly, we can say n12 will be, if the case is reciprocal, it will be velocity of light in second medium compared to velocity of light in first medium. Again, if the refractive index, the number is bigger, in any case, if the number refractive index of any medium with reference to, if refractive index in this case for a medium pair, we can say, if n21 in this case is a bigger number, it means V2 is smaller. So we can say it indicates that light is slowing down, which we have already proved. And in this case, what we can say, if n12 is a bigger number, means refractive index is smaller, then we can say the V2 is bigger, or it's a larger quantity, which is showing us that the light travels with a faster speed in the second medium. With this, we can define one more thing in place of taking a medium pair, like anything from glass to water, air to glass, something, whatever, we can define the absolute refractive index. In that case, medium 1 will always be vacuum or air, because the velocity of light is very much a constant, 3 into 10 raised to 8 meter per second for vacuum and air. So in that case, it will be called the refractive index of the material. The one medium is air or vacuum, will be C, velocity of the light in medium 1, and the velocity of light in the given medium. So this is refractive index, absolute refractive index of any given medium. Here if I am saying, understand, like for the glass, if refractive index is 1.5, what it implies that light travels 1.5 times faster in vacuum compared to glass. Clear? 1.5 refractive index means velocity c is 1.5 times. So if we are taking refractive index of glass to be 1.5, in that case we can say c is equal to 1.5 times b, velocity of light in the glass media. And otherwise case, if we get refractive index to be smaller, then the velocity of light will be faster in the given medium compared to the velocity of light in vacuum. Another way of understanding refractive index is through optical density. All these are not different from each other, but they can define the same phenomena with a different point of view. Optical density of a medium, when we talk about, so simply with our previous discussion, we can say higher refractive index means slower the light travels, and we will call it optically dense material. Okay, higher refractive index means optically denser medium where the light will travel slowly, and the other way around will be lower refractive index means the velocity of light in that medium is fast, and we will say it is optically rarer medium. So in general, optical density and mass density go hand in hand. Like, we can say denser medium, the light will travel slowly, but this is not the universal case. So as in the case of kerosene, if we take, we know that kerosene is lighter than water. It is rarer than water in general terms of mass density, but when it comes to optical density, it's other way around. Take the example of kerosene. We know that kerosene is lighter than water. Its mass density is less than water. But when it comes to optical density, it has got higher refractive index than water. So it is optically denser than water. With all this discussion about refractive index and understanding of all those phenomena, we can say when light enters from optically denser medium to optically rarer medium, means here velocity of light is less, and this is higher velocity. Light will travel faster in this medium. So in this case, you will agree that light will get faster in the other medium and it will move away from the normal. Okay, so in this combination, the light bends away from the normal. Example we have seen, like if it is glass and it is air, as in the case of glass slab, when light is emerging from the other side, from the slab to the air. And the other case if we take, when it is entering from a optically rarer medium to optically denser medium, what will happen? Optically rarer means velocity is higher, light velocity higher in this medium, and it slows down. So with our discussion and analogy, we can say in this case, optically rarer medium is air, optically denser medium is glass or water. So light will alter its path and it will bend towards the normal. It will cover the larger distance in the rarer medium and it will try to take the smaller path in the denser medium. So light, in this scenario, light bends towards the normal.